Let's discuss our first classification algorithm, k-nearest neighbor. K-nearest neighbor is one of the simplest classifiers in the machine learning toolbox, and it has a very simple principle. If we want to classify a new point, so if we want to assign a label to a new point, we do this according to the closest training points to the nearest neighbors in the training set. Since there are no real parameters here to be tuned, k-nearest neighbors is often called a non-parametric method, also an instance-based learning method, since everything depends on the training instances. So to give an example, the simplest example, a nearest neighbor classifier, which is just a special case for k equals 1. So here we have a training set of 7 points, and 4 of these points have a positive label, here shown with blue, and 3 of them have a negative label, here shown in red. And now assume we have a test point and we wish to label this point. So the first step is that we find the nearest neighbor in our training set. So this would be this point here. And we simply assign this point the same label as the nearest neighbor. So the red label or the negative label here. So this is the nearest neighbor classifier, and we can extend this to the k nearest neighbor classifier. So the idea is, rather than looking only for one nearest neighbor, we would look for the k nearest neighbors and then label the new point according to a majority vote among these k nearest neighbors. So this leads to a stabler decision and essentially averages data noise. So recall that our data is actually random. It's drawn from some random distribution, so from some probability distribution. So data is random, and maybe by chance it just happens that a training point with the wrong label just shows up as your nearest neighbor. So it's in order to make this decision more stable, we extend this to many neighbors, so and essentially average out these random effects by doing a majority vote. So if we have only 2 classes, so a binary classification problem, then the number of neighbors we consider should be an odd number. And here's the question, so why is this a good idea for binary classification? In order to illustrate the principle, so let's revisit the case for k equals 1. We had that on the previous slide. So if we have only one nearest neighbor, so like here, this is our nearest neighbor, we assign the red label here. So for k equals 3, so if we consider the k nearest neighbors, so this for this point, this would be these 3 points here. So we look for the 3 nearest neighbors, and now we do a majority vote of the label. So we have 2 red labels and only 1 blue label. So we would assign a red label here again. For k equals 5, we look for the 5 nearest neighbors. So this would be these points here. And now again we do majority vote, and we see there are 3 blue nodes and 2 red ones. So now we would assign a blue label here for this test point. So you see that k and n depends on this parameter k. So the actual classification depends on this parameter k, and this needs to be chosen well in practice. So k and n is quite simple and intuitive, but it has also nice theoretical properties. So it's, in some sense, it's theoretically sound in the following sense. Assume that we have n training points, and now we get more and more and more training points. So like n goes to infinity. So we get, in the limit, we get infinitely many training points. And assume that also we increase our parameter k to grow to infinity. So our training points grow to infinity, but also the number of neighbors we consider grows to infinity. But the number of the data points grows quicker. So grows quicker than k in the following sense, that n over k goes to 0. So both n and k go to infinity, but n over k goes to 0. So if these properties hold, then it can be shown that k and n converges to the base optimal classifier, which we had in the last section. So which is essentially the ideal classifier, the classifier with the least chance of misclassification, or with the least number of misclassifications on a very large test set. So this is a very good properties. So like we said, that the base optimal classifier is more a theoretical concept, but we see that even something simple like Knn converges towards this perfect classifier in the limit. So given these conditions here. So a classifier which does this to recover the base optimal classifier in the limit is generally called a base consistent. So in a nutshell, Knn is base consistent, which is very good. This is a good property. And this already concludes this section. So we discussed Knn. It's a very simple principle. Just predict according to the majority vote of your k nearest neighbors. And so since we have the notion of near, close, we are always working with some distance metric here. So we didn't talk much about here. So often you assume that this would be Euclidean, but in general it pays off to think about a good distance measure for Knn. We've discussed Knn in the classification setting, but it can also be immediately extended for regression. So if our target is not a discrete class value, but a continuous real number. And now, instead of majority vote, what do we have to do? So how can we modify Knn to work for regression? So the training of Knn is simple. Simply we have to store our data set. So there's no real training phase, simply store away the training set. Prediction, however, has now a computation cost of O(n), so we need to parse our training examples in order to find the nearest neighbors for our test points. So, and this can be, while this doesn't really look too bad, but this can be pretty costly if n grows very large. And so here's another question for you. How can we actually reduce this prediction time? So here's a hint. Maybe we can do something smart during training. So maybe we can sacrifice training time rather than only dumping our data set in our database. Maybe we can organize it in some data structure and therefore reduce prediction time. And I would invite you to think a bit about this. So how can we bring down prediction time? As said, Knn is a so-called non-parametric method, so since there are no tuning parameters here, but everything depends on the training data. And it has a very good property of base consistency under certain conditions.